let's take a look at section 7.3, which is on the central limit theorem. And we started talking about this a little bit today in class, but I want to get a little bit more into what it is and how it's used to solve different types of problems. So the central limit theorem, first of all, what are the objectives? It's used to estimate proportions in a population. If we don't know what it is for population, we might use the central limit theorem to help us estimate it. We may also use it to estimate, or I guess make predictions about what we think would happen in a sample. So if we, like, what are the chances that a particular sample is going to be between this proportion and this proportion, for example. And we'll do examples of all of these so you can see. It tells us that if some basic conditions are met, the sampling distribution for that sample proportion is going to be approximately normally distributed. So it's going to follow a normal distribution, which is going to help us to estimate some probabilities that we need. So what is the central limit theorem? It says if we take a random sample from a population, and if the sample size is large, and if the population size is much larger, and we'll be more specific about those in just a minute, then the sampling distribution of p hat is going to be approximately normal. It's going to follow a normal distribution with a mean of p and a standard deviation using that formula we used today in class. P, square root of p times 1 minus p divided by n. And there's going to be some situations later where we don't know what p is, and we're trying to estimate what p is. And so in that case, we'll substitute the value of p hat in its place. And we'll talk about that more in the next section. So there's three conditions that have to be true in order for the central limit theorem to apply. The first is that the sample has to be done randomly. So it has to be a random and independent sample. And in our examples, we're going to be told most of the time that the samples are done randomly. The sample has to be large. So it has to be a large sample. How large does it need to be? It needs to be large enough that we can expect at least 10 successes and 10 failures. So in other words, the number of successes we would compute as n times p, whatever the population proportion is. And then the number of failures would be n times 1 minus p, the complement. And then finally, the population needs to be large enough so that if sampling is done without replacement, the population must be at least 10 times the sample size. All right. And in our examples, most of the time the population is going to be something really large, like all people in the United States, or all people in the state of Florida, or all people on a college campus, or something like that. Most of the time our population is going to be large enough that this shouldn't be a problem. There might be some situations where if your population is small, take our college, for example. If our population is not smart, if our population is only, say, 2,500 students, and depending on the size of our sample, that may not be large enough. But most of the time, our population is going to be large enough, so that won't be a problem. So it says the figure below shows the sampling distribution of p hat for 10,000 samples of size 10. So what we did is we pulled a sample of size 10, sample, over and over again, 10,000 times. We know that the population proportion is 63%. It says, note that this does not satisfy condition 2 of the central limit theorem. So condition 2 says that we have to have a large enough sample to expect at least 10 successes and 10 failures. Well, that's not the case here. We only have 10 total. So n equals 10 is not going to be large enough. The sample size is too small in this case, and so the distribution is not normal. Now, it's got some other distribution. I don't know what it is, but I know that the distribution for these samples, sample, over and over again, it's not going to follow a normal symmetric distribution, and that's what we need. And here's a picture of what this would look like. It almost looks like it might be symmetrical, but the bottom line is it's got to follow this rule. So in the long run, we can't assume anything unless it follows these three conditions. So the next example, it says, show that the sampling distribution p hat for 10,000 samples. This time, we're looking at samples of size n equals 100. Same population proportion is 63%. This does satisfy the sample size condition of the central limit theorem, and so the distribution is going to be approximately normal. It does satisfy it because the sample is now 100. It says, why does this case satisfy the central limit theorem? Let's actually go through and test all three of those conditions. Now, they didn't tell us that the samples were done randomly here. I'm going to assume that these were because this was taken from our example the other day, that simulation I was doing where we're using the applet, and the applet was pulling random samples. So we're going to go ahead and assume that this is a random sample, and so we're okay for that first condition. The second condition involves the sample size. So let's go through that real quick just so we can see how to test it. The expected number of successes is going to be n times p. So in this case, that's going to be 100 times 0.63, right? Because our p is 0.63. So that would be 63, which of course is greater than 10. And then the expected number of failures, that's really just going to be the complement of this. So n times 1 minus p, or 100 times 1 minus 0.63, which is 37, which of course is greater than 10. And then the population, if you remember, this question came from the number of video game consoles that have been sold worldwide. So remember, this was the number of video games consoles sold worldwide. So of course that's going to be large enough. That population is going to be more than 10 times the sample size is what needs to happen. This needs to be right here, at least 10 times the sample size. So the sample size is 100. Of course, that's going to be more than 10 times the sample size. So if our population needs to be at least 10 times the sample size, so 10 times 100, of course, the population is greater than that. So we are good on the population. Now it asks us to compute the standard error. So our standard error, using that formula, remember, it's going to be p times 1 minus p divided by n. So in this case, that's going to be the square root of 0.63 times 1 minus 0.63 divided by 100 for our sample size. So I'm going to get my calculator out. And remember, to do this, we do 1 minus 0.63 times 0.63 divided by 100. And then don't forget to take the square root at the end. That's probably the most important part. That gives me approximately, here it is, 0.048 in decimal form, 0.048. All right. Let's look at an example here. So according to the Washington Post, it was estimated that 36% of Americans in 2016 owned guns. Suppose a random sample of 500 Americans is taken. All right. So first of all, who is our population? So our population in this case would be all Americans. That's who we're interested in studying. The sample is the 500 that were randomly selected, a random sample. Is 36 a parameter or a statistic? All right, so this is an important point to make. This 36%, it was estimated that 36% of all Americans own guns. So we're talking about all Americans in our population. We've estimated that 36% own a gun. So therefore, we're talking about all Americans. That means we're talking about a parameter, right? And so the symbol we would use for that is p equals 0.36. So p would be our parameter. Is 500 a parameter or a statistic? So 500 is your n value, right? N is your sample size. That's 500. It's a measurement on the sample, which means it is a statistic. Is the sample random and independent? Yes. As long as I tell you the sample's random, you're good enough to go. Is the sample large? So 500 should be good enough. We don't have to worry too much about that, but let's just go through the motions just to make sure we understand where that's coming from. The expected number of successes, remember, it's going to be n times p. So that's going to be 500 times the 36%. And I can calculate that number. I'm not sure what it is here. Let's do it. 36% of 500 gives me a value of 180. Certainly, that's more than 10. We're good to go. The expected number of failures is going to be n times 1 minus p. So in this case, that'll be 500 times 1 minus 0.36, which would be 64% of the 500. So it's just 320. Notice that that's just the rest of the sample, right? Everybody in the sample is either a success or a failure. So if 180 people we think will own a gun, that means 320 people in that sample will not own a gun. So those are, whatever the rest of it is going to be whatever the expected number of failures is. But there's the math, so you can see where I'm getting those numbers from. The third case, remember, is the population size. Is it reasonable to assume that there are at least 10 times 500 or 5,000 gun owners in the population? You know, I actually think there's a mistake here a little bit. This shouldn't say gun owners. The population isn't gun owners. The population is all Americans. So back up here, we said the population is all Americans. So what we need to have happen is that all Americans need to be at least 10 times the sample size. So this should say all Americans, right? Our population is who we're talking about. So is it safe to assume there are at least 10 times 500 Americans in our population? Where is that coming from? That's 10 times your sample size. That's 10n. And so in this case, that would be 5,000, which of course, there's more than that. There's way more than that, obviously, in the entire population. So yes, we are good to go there. So are the conditions for the central limit theorem met? Absolutely. All right, so based on the central limit theorem, complete the following table regarding your sampling distribution. So since we know the central limit theorem applies here, that means we are looking at a normal distribution. So we know that this is going to follow a normal distribution. The mean for our distribution, so the mean, remember, and this notation, I went over this a little bit in class today. The mean, we use the symbol mu for mean, and I'm using a little subscript p hat to say that I'm talking about the mean of the sampling distribution. The mean is going to be what we think is true for the original population. So the original p, remember, was 36%. So that should be the same for my sampling distribution. Now, the standard deviation, sigma, is my standard error, is really what that is. And so that we have to compute. So that's going to be p times 1 minus p divided by n, which was 500. So I'm going to get my calculator out here and let's compute those numbers. So we've got 1 minus 0.36 to begin with times 0.36 again, divided by 500. And then we're going to take the square root of that. And I'm getting about 0.021466. Let's round it to, I don't know, let's do 3 decimal places, 0.021. So I'm going to say my standard deviation is about 0.021. What does this tell us? That means that we expect each sample to contain about 36% gun owners. So on average, if we pull a sample of 500 people, we expect about 36% to be gun owners. How much is that going to fluctuate from one sample to the next? So remember, we did this in class today. The standard error tells you what the fluctuation from one sample to the next is going to be. In a percentage, this is about 2%, about 2.1% fluctuation. Could be a little higher than 36, could be a little lower, but on average, it's going to fluctuate by about 2.1%. That's what we're saying. So the question says, what is the approximate probability that the proportion of gun owners in our sample will be more than 45%? Notationally, let's write that out. So we're looking for the probability. So remember that notation from chapter 6, the probability that a given sample, so p hat, will contain more than 45% gun owners. And that's what we're trying to figure this out. I'm going to go to StatCrunch in a minute to actually compute the probability, but let's graph what we're talking about here so we know what to look for in StatCrunch. So this is my normal distribution. I expect 36%. My mean right here is 36%. So that goes right in the middle, just like it did back in chapter 6. I'm looking to see if I get more than 45%. So 45% would be down here somewhere. So more than 45% means I'm looking for a shaded area right here. And that is the probability that I need to calculate. And we're going to use StatCrunch to figure that out. What we're going to put into StatCrunch is our mean of 0.36 and our standard deviation of 0.021. So let's go to StatCrunch here. And I'm going to go, if you remember how to do the normal calculator from the last chapter, we go to Stat, and then we go to Calculator, and then we go to Normal. And then I'm going to leave it on standard, and I'm going to put in a mean of 0.36. And my standard deviation was the standard error that I calculated, 0.021. And I want the probability that we are greater than, not 0, greater than 0.45. That's the question. And I'm going to click Compute. And actually, in my picture, I had it drawn so that we could see the 0.45, but really 0.45 is pretty far out into the tail. And you can see it's so far out into the tail. Look at the probability. The likelihood of getting a sample with more than 45% of people who say they own guns, according to the way we're running this survey, is going to be right here. And that's going to be this number right here. So 0.000, whatever this number is. Let me see. 1, 2, 3, 4, 5 zeros, and then 911. So it's a very, very, very small probability. Very, very unlikely. So that's going to be about 0.0000911. So almost nothing, really. It's pretty unlikely we would get a sample that's that extreme. All right, let's look at the next example. In a closely contested Senate race, polling indicates that 50% of voters are in favor of a certain candidate and 50% are against the candidate. Suppose a random sample of 80 voters is selected. Who is the population? So our population in this case is going to be everybody that's voting in the district, right? So let's see, our population could be all voters in it's a Senate race, so I don't know. I'm just going to say in the district, whatever that is. I don't know if this is a city or a state Senate or a national Senate. Maybe it's a state. I don't know. They didn't tell us that. But we know that it's all voters in the district, whatever that is. So our sample is the 80 voters that was randomly selected. Is 50% a parameter or a statistic? So polling right now indicates that we think 50% applies to everybody that's going to turn out and vote in that district. We think 50% are going to vote for this candidate. So that means that 50% is a parameter. And so the symbol we're going to use is P. So P equals 0.50. Is 80 a parameter statistic? Well, 80 describes our sample, so that means 80 is a statistic, and that's the sample size, so that's N. 80 is N. What percentage of the sample then would we expect to favor the candidate? So we expect, because it's a random sample, we expect that whatever is true for the population is going to also be true for our sample. So we expect about 50% to vote for the candidate that we're interested in, okay? Is the sample random and independent? Yes, as long as they throw that word random in there, then we're okay by saying it's random. Is the sample large enough? So let's take a look. So large enough means that we need to have it large enough to be at least 10 successes and 10 failures. So remember, N is 80. So let's see. So the expected number of successes then is going to be 50% times 80, which is 40 voters that we think will support the candidate, which is more than 10, so we are good to go there. And then the expected number of failures would be 50%. Again, you see where I'm getting that from. It's just the complement, 1 minus, but it's going to be the same number, also 40, so we are good to go there. Is it reasonable to assume that there are at least 80 times 10, or 10 times 80, 800 voters in the population? Yes, so our population, I think it's safe to say there would be at least 800 voters voting for a Senate race. So therefore, are the conditions for the central limit theorem met? Yes. So based on the central limit theorem, let's talk about the shape. So we know that the sampling distribution is going to follow a normal distribution, and we know that the mean for the sampling distributions is going to be the same as what we expect to be true for the population, which was that 50%. Our standard error then is going to be, remember this is your sigma for your sampling distribution, it's going to be the square root of 50% times 1 minus 50% divided by n, which was the 80. So let's get our calculator out. Let's figure out what that number is. So I'm going to do 1 minus 50%, of course, is 50 times 50% again, divided by 80. And then remember to take the square root of that, and I'm getting about what was that number? It was 0.0559. I'm going to round it and say 0.056. All right, then it says, what is the approximate probability that the sample proportion will fall within 2 standard errors of the population value of 50%? So there's actually, we can answer this without doing any calculations. We could go into StatCrunch and we could figure out what 2 standard errors are on either side. But before we do that, what I want to remind you of is the empirical rule. And if you remember what the empirical rule was, the empirical rule said as long as you have a symmetric distribution of any kind, that 95% of the data would fall within 2 standard deviations of the mean. Well, 2 standard errors for us in a sampling distribution is 2 standard deviations of the mean. So if the mean is 50%, we expect it to be 50%. 2 standard deviations of the mean, or 2 standard errors of the mean, according to the empirical rule, would be 95%. And that's it. So there's nothing else to calculate there. It's going to follow the same empirical rule we've been using all semester. That doesn't go away. All right, and then it said, would it be surprising to find that 75% of the sample would be in favor? So in other words, if I were to poll 80 people and ask them who they're voting for, would it be unusual or surprising to find that 75% of them actually support this candidate? And that's what we need to figure out, okay? So let's draw a quick little sketch of what's happening here. So we know we're looking at a normal distribution. The mean goes right in the middle, so the mean, or what we expected, was 50%. So 75% is going to be out here somewhere. There's a couple of different ways we could figure this out. We could go into StatCrunch and we could actually compute the probability. That would not be an issue. Another way we could do this, though, is to think about how many standard errors away from the mean are we if we're sitting at 75% and the mean is 50%. Remember early in the course, we said anything above or outside of 2 standard errors was considered unusual. So what we need to do is figure out what do these numbers need to be 1, 2 standard errors above this mean of 50%. And the way we're going to do that is we're going to go back up here, we're going to look at this number, and I'm going to add this number to the mean of 50%. So let's do that. I'm going to take the mean, so the mean was 50%, so I'm going to add 50% plus 0.056, and I get 0.556. So 1 standard error above the mean would be here. So this is 1 standard error above the mean. Let's do one more. Let's do 2 standard errors above the mean. So I'm going to add another standard error, and I get 0.612. So then here, 0.612 would be 2 standard errors above the mean. So what was I interested in? I was interested in 0.75. So is that more than 2 standard errors above the mean? Yes, that would be surprising. Yes, since 75% is more than 2 standard errors above the mean. And so the same rules we used earlier in the course to look at the empirical rule, we're going to use those same rules now, and that's exactly what we're talking about. So anything outside of 2 standard deviations or 2 standard errors, same idea, is going to be considered unusual. All right, let's look at this next example here. It says the central limit theorem. Oh, here we are. They're just summarizing what we just talked about. So if conditions for the central limit theorem are met, the probability that a sample proportion will fall within 2 standard errors of the population value is 95%. So the same empirical rule we've been using earlier in the course, we're still going to use. So let's do another example. According to NPR, 52% of Americans own stock in 2016. Suppose a random sample of 200 Americans is taken. Would it be surprising to find that 45% of the sample owns stock? Why or why not? All right. Is the sample random and independent? They said yes, they said it was a random sample, so we are good to go there. Is the sample large? So 200 Americans was taken. I'm going to skip the details for this for now because I think you probably get the idea, but if N is 200, that is certainly large enough to have 10 successes and 10 failures. If my probability of success is 0.45, P is 0.45. Let's jot that down. N is 200. And then finally, the American population is at least 10 times the sample size. Of course, 10 times 200 is 2,000. The American population is certainly more than 2,000 people. So the conditions are met for the central limit theorem. So then let's go ahead and calculate the standard error. So the standard error using that new formula, it's going to be the square root of 0.45 times 1 minus 0.45 divided by 200. Make sure you see where I'm getting these numbers from. N was 0.45. I'm sorry, N was 200. P was 0.45. So let's go ahead and figure out what that number is. Let's see. 1 minus 0.45 I'm sorry. You know what? I just noticed something. I'm using the wrong number. P is not 0.45. Let me read this question again. It said, would it be surprising to find 45%? So scratch that. Let's make that change. So let's read the question a little bit more carefully. I was jumping the gun here. So P is not 45%. P is 52%. According to NPR, 52% of all Americans own stock. So our P would be 52%. We think all Americans that own stock, it is 52%. So 52% is what we should be using here. So let me go back here and fix this. And 52%, by the way, is what we would have used to compute our number of successes. I skipped that part, but that's what we should have used. So let's see. So we've got 52% here and 52% here. So let's go ahead and get our calculator out. So we've got 1 minus 0.52 times 0.52 again, divided by 200. And then we get the square root, which is going to be 0.0353. We'll use 4 decimals this time, 0.353. The sample proportion, that's what made me catch my error. Then they asked for the sample proportion. So the sample proportion they're interested in is the 45%. So our sample proportion, P hat, is 0.45. Would it be unusual to find a sample with 45%? So in other words, let's do it the way we did the last question. Let's draw a little sketch here, and let's figure out what 2 standard deviations away from the mean would be. So let's make a picture here. Let's try to give myself a little bit more room here. So sorry, this is a little bit asymmetric, but you get the idea. So in the middle, our expected value is 52%. We expect 52% of our sample to own stocks. 45%, now where does that fall? Now 45% would be down here somewhere. So I need to figure out what is 2 standard deviations or 2 standard errors below the mean this time instead of above. So I'm going to take my mean was 52%, and if I subtract 1 standard error, I get a value of 0.4847. I'm going to round that just because I'm short on space here. I'm going to say 0.48. So I'm going to put 0.48 here, and then let's go 1 more standard error below. So I'm going to subtract the number again, 0.0353, and I get 0.4494, which is right about 45%. 0.4494 is actually a little bit lower, so I'll set that down here. So 0.4494. So this is definitely not symmetric. Let me clean this up a little bit. Let me make these numbers a little bit cleaner so you can read them. All right, so let's give that another try. Let's go ahead and let me draw my line here. All right, so about 0.45 was what we were questioning, whether that was unusual, and then 2 standard errors below was 0.4497. So would 45% be unusual? No, it just barely makes the cutoff. I don't think I'd give you a question on a test or a quiz where the number I'm asking about is right at that tick mark. That's exactly, if we were rounding it, exactly 2 standard errors below the mean. But we'll go with it. We'll say that this just makes the cut because it's inside of 2 standard errors. So would this be unusual? We'll say no, since 45% is just barely still within 2 standard errors of the mean. And I apologize, my dog is barking in the background. So if you hear my dog, that's what it is. Well, of the mean. Let's try that again. Of the mean. And what I mean by mean, I mean the 52%. It's still within 2 standard errors of the mean, or what we would have expected. So no, this would not be unusual. Let's do one more example. According to the CDC, the percentage of adults who smoked cigarettes in 2016 was 15.5%. So let me go ahead and write that down. We really should get in the habit of writing this down as we read the questions. That means P is equal to 15.5%. Suppose we take a random sample of 876 adults. So N is equal to 876. We find that 118 of them smoke. We'll come back to that number in just a moment. Assuming the CDC figure is accurate, find the probability that if we were to take another random sample of 876 adults, the sample proportion would be greater than or equal to that 0.1347. So what they're looking for is the probability that if we were to take a sample, the sample proportion would be greater than 0.1347. That's the question. Now, that number might seem a little bit random, but what they're getting that from is the p hat. 118 of our original sample said they were smokers. So the p hat based on that 118 number, I think is that 13%. Let's double check it here. So 118 divided by 876. Yeah, that's where that number is coming from. So the p hat that they found in the original sample was about 13%. So they're saying if we were to repeat this and do it again, if we were to take another sample, would it be unusual, or what is the probability rather, that we get another sample that's greater than or equal to that 13% number? So let's do a few things here. Let's go ahead. Does the central limit theorem apply? I'm going to skip the check for now. It does apply. Certainly 876 is large enough. Certainly the population of all adults in the United States is large enough. And it was a random sample. So yes, the central limit theorem applies. So no problem there. Let's go ahead and draw a quick picture of what this looks like. Now we're looking at a normal distribution. In the middle is what I expect. So my expected proportion of smokers is my population proportion. I'm going to write this as a decimal and put 0.155. So that's the 15.5%. And then 13.47%, or that 0.13 number, is over here. And they want to know what is the probability that our sample proportion will be greater than that number. So greater than that number means we're looking at all of this shaded area. Now, before we go too much further, I have to compute the standard error. I have to know what the standard error is for StatCrunch. So to compute the standard error, I'm going to do my population proportion times 1 minus my population proportion divided by the 876 number. And let's go ahead and put that into our calculator. You've always got to compute the standard error because that's the standard deviation you're going to use in StatCrunch to compute your probabilities. So times 0.155 divided by 876. And then we're going to take the square root of that number. I'm getting 0.01. I'm just going to say 0.012. I'm going to round that off and say 0.012. So let's go into StatCrunch and let's put our information. Let's make sure we see where everything goes. So let me reset this. And then I'm going to leave it on standard. Now, the mean is what we expected for our population. So the mean was the 15.5%. So we're going to go 0.155 for our mean. The standard deviation is the standard error that I just calculated, the 0.012. And we want to know what is the probability that we will get a sample greater than, what were we interested in? It was the 0.1347 number. So 0.1347 and click compute. And notice that matches what I shaded just a second ago, which is a good thing. And so I'm getting a probability of that occurring about 95%, 0.9546, something like that. So the probability that we are above that 13% mark is about 0.954. So it's a pretty high likelihood that if we select a random sample of 876 adults, more than 13% of them are going to smoke.